I'm going to tell you something about dynamics of space vehicles this morning. I hope this will be a pleasant morning for you. I have divided this lecture in two parts. So basically the first part is a rather popular lecture on orbital mechanics, which introduces you in the dynamics of space vehicles and the physics behind, without any maths or not too much maths in this part. In the second part, if anybody is interested, we can have a more detailed look into dynamics of space vehicles. We can also do some mathematical analysis and derive some formula if you're interested. However, this is rather something for those who are familiar with basic calculus and differential equations and so on. So the first part will be about 90 minutes and should be it should be able for you to follow every part here, because I have held this lecture many times for people who are not involved in physics or in mathematics. Well, nevertheless, I will give you some, as I think, interesting information about a trip to Mars. I will show you the basics of orbital mechanics at the example of a trip to Mars. We will answer some questions. Oh, that's here. How are space vehicles moving is the first one. Then I will answer the question how space vehicles can be controlled actively. I will show you how we can get to Mars. How long does it take to get there? We will learn when we can start to Mars and which amount of fuel is necessary for this trip. So these are the basic questions which I will answer in the next 90 minutes. But first of all, maybe I should introduce myself a little bit to you. My name is Wolfgang Steiner, as Franz Daschel has already mentioned. I'm here professor for mechanics. So all these questions are strongly related to mechanical engineering and the field of mechanics. I've studied at the Technical University in Vienna, mechanical engineering. And I focused, at the end of my studies, I focused on satellite dynamics and wrote my PhD thesis on this topic. Also my habilitation thesis is on the stability of space vehicles. So I've also a lecture at the Technical University of Vienna on orbital mechanics. If anybody comes to Vienna, maybe you can look at this lecture. It's all in the summer semester, every Friday in the afternoon. So I'm about 20 years of my life I have been working on satellite dynamics, and of course I've seen a lot of missions and was very interested in this topic throughout my scientific career. Well, if we want to go to Mars, then the first we should ask, the first question we should ask is, what is this for? Which object is Mars? What is this? How large is this planet? And you can see here on this slide a little size comparison of the two planets. So as you can see here, Mars is really a very small planet compared to the Earth. And the gravity is about 1/3 of the Earth. It has a very thin atmosphere. So it's really a strange surrounding there. And if you would really go there, you would find a completely extraterrestrial surrounding, which has very little to do with our Earth. But nevertheless, it's an interesting object, and astronomers are asking if there is life on this planet. So there are lots of motivations to go there. Actually, up to now, we only sent robots to the surface of Mars, no humans. As we can see maybe at the end of this lecture, there are very natural reasons why humans have never been traveled to Mars before. It's simply a question of fuel. We can go there, but it's not possible up to now to return from Mars to the Earth. That would cost an enormous amount of fuel, which is up to now not feasible. Nevertheless, there have been missions, Mars missions of robots, which sent very impressive pictures from the surface of Mars, and some of them are shown here. Of course, you know this from TV or from the internet. If you are interested in space activities, then you certainly have seen such a picture. Okay, I showed this already. Well, Mars is one of 8 planets orbiting around the Sun. Here this list shows the planets of our solar system. The last object here, Pluto, is actually not a planet now. It has been a planet up to, I think, 5 years ago. But then the International Astronomical Association decided that Pluto is not a planet. And so we actually have 8 planets. Unfortunately, this is a German table, but maybe you can, also the labels here will be understandable, but these parameters here is not very difficult to understand. 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. We have here the so-called semi-major axis. That's basically the distance of the planet from the Sun. And you can see our Earth is the 3rd planet at a distance of about 150 million kilometers from the Sun. And Mars is about 228 million kilometers away from the Sun. It's the closest planet to Earth. So that's why it is the first object which became interesting for astronomers and also for the orbital mechanics, because it's rather close to the Earth. What we can observe additionally is that all the planets are in the same plane, are orbiting in the same plane about the Sun, around the Sun. You can see here the so-called inclination of the orbit of each planet. We have a reference inclination of the Earth. Here you see 0. That means we have a reference plane called the ecliptic plane, and all other planets are moving in planes which are slightly inclined, about 7 degrees for Mercury, or we have for Mars about 2 degrees. So, but basically this is a very small angle, and all planets are nearly in the same plane. And the only exception here is maybe Mercury, which is has an inclination of 7 degrees. Also, the eccentricity of the orbits of the planets are nearly 0. Eccentricity 0 means that this is a circular orbit. High eccentricity means that this is a more elliptical orbit. As you can see here, Mercury has a remarkable eccentricity of 0.2. So you can see here, if you look at the right picture on the top, that this is really an elliptical orbit. It's not very good to see, but maybe you can see it. This is really an ellipse, but and also Mars has an eccentricity of about 0.1, as you can see here in the 4th line of the table. So also here you can see that this is an elliptical orbit. All other ones, all other orbits are nearly circular. The right picture here shows the inner solar system, consisting of the small solid planets, Mercury, Venus, Earth, and Mars. And the outer planets are seen here. You see that the inner solar system is a very small caption here in the left picture. It's this square here. Within this square, this is the zoom of shown in the right side of the picture, of the slide. And as you can see here, the outer solar system is very large. And if you look at this here, Neptune has a semi-major axis of 5,000 million kilometers, or 4,500 million kilometers. So that's really a huge dimension. And these planets are usually gas planets, so that's have no solid surface, apart from the last object here in the slide, Pluto. But we know that I've already said that this is not counted as a planet anymore, but this would be a solid object again, and it's a very small planet. But that's also the reason why it is not counted as a planet anymore. Well, the physics behind the solar system is described by the 3 Kepler's laws. Maybe you're familiar with that. If you're engineering students, then I think you will have heard this in some lecture. The first law formulated by Kepler is the law that every planet orbits the Sun on an elliptical orbit. The Sun is located in the focus, in one of the 2 foci of the ellipse. And the second law is a statement about the velocity of the planet. It states that the line segment joining a planet and the Sun sweeps out equal areas during equal time intervals. So that means if you are looking at the swept area within a specific time interval, then this is always the same when the time interval is the same. So if the planet is moving from this position to this one, then we have here an area which is exactly the same as this area when the time interval from here to here is the same as from here to here. So that means that the planet accelerates if it approaches the Sun, and it decelerates when it is far away from the Sun. Well, and the third law of Kepler is a statement about the total orbital period of the planet. It states that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. The semi-major axis is the half of the diameter of the orbit, so it's actually this distance here. And this distance is related to the orbital period. And if you compare 2 planets of the solar systems, then we have then the square of the orbital period of 2 planets or the relation between the square of the orbital periods is proportional to the relation of the cubes of the semi-major axis of the 2 orbits. So that means planets closer to the Sun are moving faster than planets which are outside or far away from the Sun. Well, in orbital mechanics, satellite dynamics, Kepler's laws are of course valid again, but the difference is that we don't have Sun and a planet, but we have a so-called celestial body and a satellite. And of course there are different possibilities for the celestial bodies, which could be interesting. For example, a satellite could orbit around the Earth, of course. That's the most common application. Then we have orbits around the Sun, orbits around the Moon, orbits around another planet, or orbits around another moon. Moreover, we have not only elliptical orbits here, but also hyperbolic orbits. So this orbit, if this is a satellite, might also be a hyperbola or a parabola. But of course, in most applications, we have to deal with elliptical orbits around the Earth. And I can show you here two examples. The most frequent orbits are circular orbits with zero eccentricity in a very low altitude. So these types of orbits are called low Earth orbits because they are very close to Earth, and we have typical altitudes of a few hundred kilometers here. So the satellites are traveling around the Earth in an altitude of 400 or 500 kilometers, like the International Space Station. And but there are also examples of elliptical orbits. For example, here the so-called Molniya satellite is a Russian satellite which orbits in a highly eccentric orbit, which is synchronized with the rotation of the Earth. You know, Earth rotates within 1 day around the north-south axis, and this orbit here is a so-called 12-hour orbit. So the satellite moves around the orbit 2 times each day. Please, yeah.
But if the orbit turns into a hyperbolic or a parabolic form, it actually leaves the orbit.
Yes. These are only examples for elliptical orbits. If you have a hyperbolic orbit, that would look like that here. You have, again, the Earth, and hyperbolic orbit is something of that. It's an orbit which approaches Earth in this point here, which is called the perigee. So this is the closest point to the Earth. It's called perigee. And then it escapes again from the Earth. And of course, you have not an orbital period here, because this probe leaves Earth in the space here. It comes from space and leaves the Earth in the deep space.
So this would mean that the velocity is too high to be kept by the gravity?
Yes, you could say it in this way. You can express it in this way, that the velocity reached here in the perigee, called the perigee velocity, if this velocity is too high, then you are on this orbit. If this velocity is lower, then you have an orbit of this type. And if the velocity is even lower, then you have a circular orbit. I will come back to this a little bit later. But let us first focus on the elliptical orbits. You see here the geometry of an elliptical orbit. An elliptical, here, this is one formula. I hope you like it. An elliptical orbit may be described in a by a mathematical formula. This is the so-called polar form of ellipse. Maybe you know from school the Cartesian form of an ellipse that looks like that: x squared by a squared plus y squared over b squared equal to 1. That's the usual form you know from school. But you can describe the geometry also in this form by describing the distance of the planet from the sun, or the distance of the satellite from the celestial body, as a function of the so-called true anomaly. The true anomaly is the angle theta here, shown here. It's the angle between the semi-major, the major axis of the orbit, and the line from the sun to the planet. So this angle is called, this is mathematics, it's called the polar angle. Here in astronomy, it's called the true anomaly. This true anomaly is the argument of this function, and if you describe the distance r as a function of theta, then you can locate the satellite for every angle theta, and you obtain the geometry of the orbit. The function has also two parameters denoted as p and e. P is a parameter which has the dimension of a length. It's called the semi-parameter, and you can easily interpret this parameter p. If you set theta to 0, to 90 degrees, then the cosine becomes 0, and you have r equal to p. So that means if you set the theta to p, then you obtain the distance here above or below. So this is this distance p, which appears here in the formula. The second parameter is called the eccentricity. It's a dimensionless parameter, and it's the relation of the distance of the focus f from the center of the ellipse and the semi-major axis a. So that's the eccentricity here. The semi-major axis is also shown here on this picture. You see the diameter of the ellipse is 2 times a, and of course the the half diameter is a. F is the focus. It's the distance of the center of the ellipse to the focus. Well, here the second picture shows once again the angle theta, called true anomaly. This angle describes the position of the satellite, or the angular deviation from the semi-major axis. This point here, where the satellite is closest to the Earth, is called the perigee, and and r is the actual distance of the satellite from the Earth. There are two other angles which are used to describe the position of the satellite. The first one is called the eccentric anomaly, shown here, capital E. So this angle is defined as follows. If you construct a circle around the orbit, here denoted as auxiliary circle, a circle which touches here the ellipse at the perigee and at the opposite point called the apogee. So construct this auxiliary circle which has the center here, also in the center of the ellipse, and the radius of the semi-major axis. Then you can project the position of the satellite to this auxiliary circle. Projecting means that we use this line here perpendicular to the semi-major axis, and we obtain the auxiliary point here marked as a red point. And this auxiliary point has an angle capital E with the semi-major axis. And this angle is called eccentric anomaly, and you can construct this angle capital E for every position of the satellite. This eccentric anomaly also describes the position of the satellite. However, it's a more complex angle, and but there's a third anomaly called mean anomaly. This is also an angle which is a little bit difficult to draw here in this picture, but imagine that we have a third auxiliary point moving on this auxiliary circle, but with constant velocity. So imagine a third point here moving with constant velocity around the auxiliary circle, and exactly orbits the center in the period of the satellite. So this point would move in the period of the orbit around this circle and comes back to the perigee after one orbit. So, and then this third point has at any time instance a certain angle with the semi-major axis again. This third angle is rather a measure for time. It's a normalized time because this is the angle is 0 when the satellite is in the perigee, and it's again 0 when it returns to the perigee. And in between, it takes all angles between 0 and 360 degrees. So actually, this is a measure of time in terms of an angle. Yes, please.
Is it the angle between the auxiliary point and the major axis, or
not the auxiliary point? It's difficult to visualize here. So imagine it's another point. So imagine this is we have here our ellipse. That's the semi-major axis. Here have the perigee, and then we have again already 2 points here: the satellite, the auxiliary point, and now imagine we have a third point, which travels on the auxiliary circle and starts at the time when the satellite is in the perigee. This point should also be here, and then take one orbital period. Then this point moves around the circle and comes again here.
at the same time
At the same time as the satellite. But the difference is that this point is moving with constant velocity on this circle, whereas the auxiliary point is not moving with constant velocity because the satellite accelerates here and decelerates when it travels around here. Yeah. So then we have here an angle between the center and P, and that's called the mean anomaly. And this tau is actually a measure of time. It's an angle which is proportional to the time from here to here. But it's not a time measured in seconds, it's rather a time measured in degrees. Yeah. So these are called the 3 anomalies. Maybe that's a rather unusual notion here. In satellite dynamics, there are things are different called differently compared to other engineering fields. So angles are here denoted as anomalies, and as we see later, angles are also sometimes called arguments, but actually these are angles. Well, let me now proceed. If we want to locate an orbit, so this is an orbit of a satellite around a celestial body like the Earth. If we want to locate the orbit in the space, then we have, of course, also look for a coordinate system where we can describe this ellipse. And then for that purpose, we have to have a little a look on celestial mechanics. As we have seen already, the Earth is a planet orbiting around the Sun on a more or less circular orbit in the ecliptic plane. So you can see here the Sun, here the Earth. Of course, Earth is much smaller than in this picture, but that's of course for visualizing the relations here. We can see again here the ecliptic plane. The ecliptic plane is seen here and also here. The ecliptic plane is here in the plane spanned by the x and the xs and the ys axis. So first of all, we could introduce a so-called heliocentric coordinate system. That's, for example, for interplanetary missions. If you have a satellite traveling around the sun, then you need a coordinate system like this one, a heliocentric system. A heliocentric system is defined in the following way. First of all, we could locate the ecliptic plane. That's the plane of the orbit of the Earth around the sun. This defines an invariant z-axis. So this axis z here is normal to the ecliptic plane. And we can use it as a coordinate axis to orient in the space. But then we need two more axes. Of course, we have to define one axis within the ecliptic plane. And here we look at the XS axis. This is defined in the following way. This is the direction to a specific point in the space, which is called the equinox point, the spring equinox point. That's a point defined in the deep space, and the axis is always pointing to the same position in the space. And the third axis, ys, is also shown here. It's simply perpendicular to xs and also to zx. Means, of course, it is also in the ecliptic plane. This three axis of the heliocentric system is a so-called inertial frame. Inertial frame is a frame which does not rotate and does not move. In such a frame, we can easily formulate the laws of dynamics, of Newtonian dynamics. Maybe you know the Newton law for dynamics. It's mass times acceleration equals force. And this law can only be applied in a so-called inertial frame. And this XS, YS, and ZS frame is really an inertial frame. Actually, it's not totally an inertial frame, because also the sun is moving in our galaxy, but this is a very, very slow motion with very, very low angular rate. And for practical reasons, it's absolutely sufficient to consider this heliocentric system as an inertial frame. But for missions around the Earth, for orbits around the Earth, we need another coordinates system, which is centered in the center of the Earth. And this second frame is here called geocentric system for near-Earth missions. This system has also three axes, x, y, z, and these axes are shown here. You can see xe, ye, and ze here. So how are these axes defined? These axes are defined in the following way. First, we use the axis of the Earth, the north-south axis, as the z axis. Then we have two additional axes within the so-called equatorial plane. The equatorial plane of the Earth is the plane perpendicular to the north-south axis in the level of the equator. And it's a piece of this equatorial plane is shown here. This one here is the equatorial plane. This equatorial plane intersects the ecliptic plane along a straight line here, denoted G. And we use this intersection line to define the x-axis. Of course, if Earth is now moving around the sun, take this position, for example, here, then the equatorial plane has also moved with the Earth. Also, the axis of the Earth has moved. But note that the axis of the Earth does not rotate, at least not within time intervals which we have to deal with. So this axis here is more or less stable and always points in the same direction. So at this time instance, we have at least a parallel axis, parallel Earth axis, and the equatorial plane is then simply shifted parallel from this position to this position. And we have again here the intersection between ecliptic and equatorial plane. Here, this is again this straight line G. And as you can see here in this position, that's the equinox position of the Earth. Here you see that this axis is exactly pointing along the XS axis, which we have already defined before. Well, and the third axis, YE, is perpendicular, of course, to the two other ones and completes the geocentric system. So actually, this system, XE, YE, ZE, is also nearly an inertial frame. It's just a system of axes which is shifted parallel when Earth moves around the Sun. So the axis here, these three axes, don't rotate. But the difference to the heliocentric system is that the origin of this system is not stationary in the inertial frame. It moves on a circular orbit. The origin of this system moves on a circle, but the axis remains stable, always point in the same direction. So actually, this also allows us to formulate Newton's laws in this geocentric system. Well, and for near-Earth missions, of course, we use such a geocentric system here. Now, if we are looking at an Earth orbit a little bit closer now, so you take this picture here, look at the Earth. Of course, maybe I have to mention, Earth is still rotating in this system here. Because the Earth is rotating around the Z-axis within 1 day. But the axes here are stationary. So imagine the planet rotates about the Z-axis here within 1 day. So look a little bit closer here on this geocentric system. We see again here the three axes, XE, YE, and ZE. Here you see a little bit of the Earth, which is rotating in the system. We see here again the equatorial plane. And this x-axis is again pointing to the, in German it's the Frühlingspunkt, it's the equinox, it's a special point on the deep space, in the deep space here. So you here see the positive axis, positive part of the Z-axis is on the North Pole. And now in this, we may now describe an orbit of a satellite in this plane, in this geocentric coordinate frame. And you see here an orbit of a satellite. Basically, it's the northern part of the orbit. You have to imagine that the orbit, of course, has a part below the equatorial plane, which is not shown here, to make the picture a little bit easier. What we can observe is that there are several parameters which characterize this orbit here, which describe this orbit here. So first of all, of course, we know that the orbit is characterized by its semi-major axis, or semi-axis A, or also by the orbital period, which is directly related to the semi-major axis. And it's also characterized, of course, by the eccentricity. So we already have seen these two parameters, which just describe the ellipse here in the so the dimensions of the ellipse, more or less. But of course, we need more parameters to describe how this ellipse is oriented in the space. In particular, how it is oriented in this geocentric frame here. And for that purpose, we can first describe the so-called orbital inclination. That's simply the angle between the orbital plane and the equatorial plane. Here you see this inclination angle I. this angle can be 0. If this angle is 0, then you have an equatorial orbit. So the satellite is traveling in the orbital plane. It's always above the equator. If E is 90 degrees, then you have a so-called polar orbit. So the satellite is always traveling around the poles of the Earth. Well, and more or less this angle is always the same. Of course, there are some perturbations which cause a slight motion of this angle I. So this is a little bit oscillating, but more or less it's the same. Well, so this is the orbital inclination. If the inclination is smaller than 90 degrees, we can see here in this picture that the satellite is traveling around the z-axis from west to east. So that's called a prograde orbit. It's moving in the same direction as Earth moving around its axis. Because Earth is also moving from west to east, this direction. If you take the right hand, then it's moving in the direction of my fingers. And here's the same. But if E is greater than 90 degrees, so imagine that E is greater than 90 degrees, then the satellite is orbit in opposite direction around the z-axis. So that's called a retrograde orbit. What do you think? What are the most frequent orbits? Polar or some E greater than 90 degrees, or E smaller than 90 degrees? Which one is more frequent? Yes, this is more frequent. And what's the reason for that? It's very simple. Because for these orbits, we can use the, yeah, please?
We can use the acceleration of the Earth.
Yes, we can use the velocity of the launch place of the Earth, because every point we are launching here at some point of the Earth, surface of the Earth, and this point has also a surface in the right direction. But for these orbits, we have to put additional fuel to reach this orbit. So that's the simple reason why these are more frequent. Well, but this inclination is not the only parameter. We need more angles to describe the location or the orientation of the orbit. First of all, we need the so-called argument of the ascending node. That's the following angle. If you take the intersection line between the orbital plane and the equatorial plane, you get the so-called node line here. This is the intersection line of the orbital plane and the equatorial plane. So this node line has two remarkable points. Here, this point is the so-called ascending node. That's the point where the satellite crosses the equator from south to the northern part. And the opposite point would be the descending node. It's just here, the opposite here. And if you take the ascending node and consider the angle between the nodal line and the x-axis, then you can define this angle omega, called the argument of the ascending node, or in short, rect ascension, capital omega. This angle describes the rotational orientation of the orbit around the z-axis. So we need this parameter to locate the orbit in the space. Well, then we need one more parameter. Of course, it's also necessary to say where the perigee, this closest point, is located in the orbital plane. So we could do this by describing this angle omega, here, from the nodal line to the axis to the perigee, the semi-major axis from here to here. Here we have the perigee again. If we look a little bit more in detail, then we would notice that this parameter, capital omega and small omega here, are drifting within time. So these are actually not stable parameters resulting from a perturbation of the Earth's gravity field. Earth has a rather complex gravity field. It's not a spherical gravity field because the Earth looks like that. It's not a sphere, but rather an ellipsoid. So that means that the gravity field of a planet which looks like that is much more complicated than for a sphere. And that resides in the so-called J2 perturbation. This J2 perturbation causes a drift of the parameter capital omega and small omega, but actually the inclination remains stable. This is not affected by this perturbation. Well, and there's also a third parameter. If you describe the parameter, the orbit of a satellite, then you also have to locate where the satellite on the orbit is at a specific time. So you have to define where at a reference time first, reference time, and then say where is the satellite on the orbit at the reference time. That means we could describe, for example, the true anomaly, that theta. That's the angle, the polar angle to the satellite. We have also already introduced this. And this, you could describe theta as for the reference time. Then you know where the satellite is on the orbit, and you can track the satellite in the future. Usually, it's rather usual to define not the true anomaly, but the mean anomaly, which is this one here, this angle, which is related to the true anomaly by a mathematical relation. So here I will come back to this picture now. As I have already said, we have a specific circular velocity for an orbit. For example, you can compute the velocity of a circular orbit with radius rp. This is given by this formula. G is the universal gravity constant, and me is the mass of the Earth. If we increase this velocity, then we reach an elliptical orbit. And if this orbit becomes more eccentric, if we increase this perigee velocity again, and if the perigee velocity reaches a critical value, then we arrive at the escape parabola. And here you can define the so-called escape velocity, which is necessary to leave the Earth. It turns out that this is the root of 2 times the circular velocity. And we can also give some numerical values for these velocities here. For example, if this is Earth, and if you have a perigee distance which is close to the surface of the Earth, so it means that rp is nearly the same as the radius of the Earth. We are just a few hundred kilometers above the surface of the Earth. Then we have a radius of about 6,400 kilometers. The resulting circular velocity is then 7.9 kilometers per 1 second. It's called the first cosmic velocity. And the escape velocity is 11.2 kilometers per second. So that's pretty fast here, nearly 8 kilometers in 1 second. You have to accelerate a probe to this velocity when you want the velocity, the probe in a circular, to come to a circular orbit. Well, now I have said something about circular orbits, and now we are also at escape parabolas or hyperbolic orbits. Then we can ask what happens when we accelerate a satellite to the escape velocity or beyond. Then you will see the following. A satellite starting here in the vicinity of the Earth moves away from the Earth, and at some point you can neglect the Earth because the probe is so far from the Earth that it has no more influence on the probe. But that does not mean that there's no other body. Of course, we have the Sun, which now dominates the motion of the satellite. So at a specific point, we can say that the motion of the satellite will be dominated by the Sun. By the Sun here. It's also possible to define a so-called sphere of influence where the Sun begins to dominate the motion of the satellite. So we can say within the sphere of influence, the Earth dominates the motion of the satellite. Without the sphere of influence, the Sun dominates the motion of the satellite. This sphere of influence can be defined in a very exact mathematical way. It's defined as the set of all points in space where the acceleration from the gravity of Sun and the planet are equal, are of equal magnitude. But that's something from mathematical details which I will skip here. Of course, within or during the trip of a satellite, we have here a region where the satellite is influenced by both bodies. You can't say that we have a pure two-body problems between satellite and planet, and then we have a poor problem between Sun and the satellite. So usually we have here an area where the two celestial bodies influence the motion of the satellite. Nevertheless, it's a good approximation to neglect the influence of the Sun totally within the sphere of influence and to neglect the Earth completely without the sphere of influence. That's an approximation, but this is a very good approximation, and it's in most times it's sufficient. In most cases, it's sufficient to describe the orbit of a satellite and to design a space mission. So should we have a break, or are you tired? Oh. Okay, then I will continue a little bit. So let me know if you are tired and if you should make a break. Well, for this so-called patched conic approach means that we have conic sections, hyperbola or ellipse, basically hyperbola within the sphere of influence, just resulting from a two-body problems between satellite and the planets and the Sun. But if we are here on the sphere of influence, we have to change the dominating celestial body. And at this point where we reach the sphere of influence, we have to make some transformation of two different descriptions of the motion. So what we can say is that the planet here arrives with a certain velocity, a so-called geocentric velocity, because this velocity is measured relative to the Earth. But the Earth is not stationary. It's also moving with a certain velocity, which is here colored red. And with the planet, also, of course, this point of the sphere of influence is moving with a certain velocity. So we have to add this velocity of this point here, of the sphere of influence, to the planetocentric velocity, and this determines the heliocentric velocity. And now, from this point, you can start to compute the orbit around the Sun with this starting initial velocity here at this point here. So if you follow the motion of the satellite, then you see something like that. So for your orientation, we have already learned that this distance of the Earth from the Sun is about 150 million kilometers. So recall, these are 150 million kilometers. So now we may ask, what is the radius of the sphere of the influence here? So what is the radius of the sphere of influence here? Of course, this depends on the mass of the planet. If you have the Earth, if you look at the Earth, then this sphere of influence has a radius of nearly 1 million kilometers. Exactly, it's 920,000 kilometers. So if you compare this with this distance here, you see this sphere of influence is very small in the scale of the solar system. So it's about nearly a point. This is a very small distance compared to this. So the sphere of influence is rather a point in this picture, if you would draw it in the real dimensions. Well, other planets have, of course, different spheres of radius of spheres of influence. The Mars is a smaller planet, and the sphere of influence is about 570,000 kilometers. Jupiter has a very large sphere of influence. It's 40 million kilometers. And of course, you can also consider other celestial constellations. Just imagine here, this is the Earth. And this planet is the Moon. Then you have also a system of two celestial bodies and a satellite. And in this system, we can also define the sphere of influence of the Moon, for example. Well, the concept of the sphere of influence and the so-called patched conic approach, which is shown here, enables us to understand the so-called gravity assist maneuver. I didn't change this here from German. This is a special maneuver which is necessary to accelerate a space probe in the solar system and to enable the space probe to travel to the outer planets of the solar system. So I can show you how this works. As we have learned here, we see that the sphere of influence is very small compared to the scale of the solar system. So the time within the sphere of influence, the flight time within the sphere of influence is also very small compared to the flight time here of the yellow part of the orbit. Now, look at a satellite coming from the solar system and enters now the planet, the sphere of influence of a planet at a specific point A. Then what will happen? We will have a hyperbolic flight path around the planet because the velocity is here very high and we won't decelerate here in the vicinity of the Earth. This will be a flight path like this here. We will reach here a perigee, or the closest point to the planet, and then of course we will move away from the planet again and reach again the sphere of influence at the specific point B. What we can say is that the velocities here in the point A and the point B will be the same. Because if this is a sphere, never exactly, it's not really a sphere, but it's nearly a sphere. So the distance at the point A, at the point B from the Earth is the same. So we have the same potential energy with respect to the Earth at point A and point B. The velocity here is the Earth-centered velocity. That's the velocity relative to the Earth. And so we have the same, we must have the same, also the same kinetic energy at the points A and B, because the total energy must stay constant. And if the potential energy is the same here and here, then also the kinetic energy must be the same. So what follows is that the magnitude of the velocities is also the same. So the vector VA is the same as the vector VB. At least the magnitude of these vectors is the same, of course, but we have different directions, different flight directions at the point A and the point B. But the magnitude of the velocity is the same. So now we can ask, what is the heliocentric velocities, which has the space probe at the when it enters the sphere of influence and when it leaves the sphere of influence. What we have learned from this slide here is that we have to add the velocity of the planet to the velocity of the space probe to obtain the heliocentric velocity here. So this was this construction here. We have two velocities, the velocity of the Earth-centered velocity and the velocity of this point of the sphere of influence, but actually this velocity is the same as the velocity of the planet itself, because the sphere of influence is very, very small compared to the size of the solar system. So we may simply add the velocity of the Earth here to the space probe to obtain the heliocentric velocity. That's the velocity which has the space probe relative to the Sun. And if you do this here, we see if the Earth has a velocity in this direction, that means our flight path is at the backside of the planet. Then we have to add the Earth's velocity to the velocity of the space probe, and this must be the entrance velocity here, this heliocentric entrance velocity at point A. If we now look at point B, we can make the same construction here at the point B. Then we have the velocity VB, which is the same has the same magnitude as here, but a different angle, and points in this direction. If we now add the Earth's velocity to the velocity VB, the exit velocity of the sphere of influence, then we obtain this heliocentric velocity. As you can see here, the velocity has increased a lot. What we can also observe is that this sphere of influence is nearly a point because it's so small compared to the size of the solar system. And the flight time from here to here is also very short. It takes maybe a few days, 1 week maybe. But then the probe travels around the Sun several years again. So what we can say is that the flight time from here to here is short. The distance of the magnitude of the sphere of influence is also very small. So actually, the flight time from here to here is in the scale of the solar system just an instantaneous change of the velocity from this to this, without a remarkable change of the heliocentric position of the space probe. So from this point here to the entrance point here, we have nearly the same position in the solar system, because it's very short flight time and a very short flight distance. And that means that at point E and point A and point B, we have nearly the same potential energy of the space probe with respect to the Sun. It's the same position. We are at the same position in the solar system here in point A and point B, but we have different velocities. Yes, please.
But actually, by entering the sphere of influence of the Earth, the object decelerates related to the Earth because of its velocity.
It decelerates. No, it doesn't decelerate here. Here it accelerates with respect to the Sun. With respect to the Earth, it has a velocity VA. Then it accelerates related to the Earth, and then again it decelerates. And here it has the same velocity as in the entrance point.
So how can it be that objects are crashing on the Earth?
Yes, if this angle is in a specific has a specific value, then of course it might be that this point is within the surface of the Earth. That would cause a crash. So this would be a special design of the space mission to have the perigee distance at a specific value.
A safe distance.
It should be a safe distance, or you can define this distance, and of course then you have to, this defines how, at which point we have to enter the sphere of influence. But what is always, what can always be said is that the velocity here and the velocity here will be the same. But the heliocentric velocity is quite different. Also, the heliocentric position of the space probe is the same in the points A and point B. That means that the space probe, the space vehicle, has obtained total energy, because the potential energy is the same, but the kinetic energy with respect to the solar system has increased a lot. And that's why we can accelerate the space probe in the solar system by flying around a planet. And it's called the gravity assist maneuver. You can do this also in the other way. If you fly around the planet in this direction from point A to point B, planet is again moving in this direction with the sphere of influence, then you have the construction in a different way. Then we have here a reduction of the velocity, of the heliocentric velocity, and this would decelerate the probe with respect to the the heliocentric system. So you need such maneuvers to reach the outer planets of our system, of our solar system. And here you can see a very famous example from the 19th. So the start of the probe was October 18th, 1998. You have here the launch point at the Earth. Then we can see here a flight path. The probe was sent to Jupiter, which is far away from the Earth, but the probe first moved in the inner solar system to the Venus. Here we had a flyby maneuver or gravity assist maneuver at Venus, which accelerated the probe. Then after, this was in February 1990, then after several months again, we reached again the Earth, had a flyby or gravity assist at the Earth. Then the probe accelerated again. You see the flight path after the second flyby. And then we had one more flyby in December 1992 at the Earth. And this second flyby put the space probe on an orbit or on a heliocentric trajectory which reached Jupiter at December 1995. So that's the typical mission of an interplanetary space probe. It takes a lot of time. You can see the start from here to here. This was about 6 years. Took 6 years, this travel. But of course, this was a very interesting trip because you can take lots of pictures and make observations during this trip. First of all, we had the opportunity to make photos from the Venus, at the first gravity assist maneuver at Venus. Then there were 2 flyby maneuvers at the Earth. It's also very interesting because you get the opportunity to take a picture from the Earth and the Moon, for example, to observe the whole system, Earth, Moon. It's not easy to obtain this observation position, and this was a very fine opportunity to take, for example, this picture here. Then there was also the opportunity to observe several smaller planets, asteroids, here in, for example, 1993 or here 1991. And the arrival at Jupiter was also very interesting because here we had the opportunity to observe the impact of the famous Shoemaker-Levy comets on the surface of Jupiter. Very, very famous astronomical event.
At this time, was it possible to calculate the exact point where the satellite would enter the sphere of influence of Jupiter?
Yes, it was, of course, possible to compute this, but you have to correct the flight paths from time to time. So this satellite, or this deep space probe, has also rockets which are used to correct the flight position from time to time to stay within certain tolerances. Please.
When crossing the asteroid belt, did the probe go outside of the ecliptic, or how?
No, it always
impact events.
The probe stayed within the ecliptic, more or less every time. It's really very hard to get out of the ecliptic. Getting out of the ecliptic needs a tremendous amount of fuel. You can imagine this the following way. If you have here the sun, and this is the Earth traveling around the sun, then every space probe which is launched from the Earth, of course, gets the velocity of the Earth. We can, by means of rocket thrusts, we can accelerate the probe by about 1 or 2 or a few thousand kilometers per second. But the question is, how large is this velocity? The main question is, how large is the velocity of Earth when it travels around the sun? What do you think? What is this? So it's nearly 30 kilometers per second. So if you remember our escape velocities, this was 11.2 kilometers per second. If you accelerate the probe to escape velocities, that's just a third of this velocity. So if you want to get the probe in an orbit in this way, then you have to put a velocity change in this direction, delta V, which is enormous. If you want to reach the velocity in an orbit out of the ecliptic, for example, if this is 90 degrees, then the orbit would be perpendicular to the ecliptic plane. Then this velocity must be root over 2 of v. So that's 45 kilometers per second. So you can't reach such an amount of velocity change with a rocket thrust. That's absolutely impossible. The only way to get a space probe out of the ecliptic would be to use such a flyby maneuver. But it's also very difficult. But we are lucky because all our planets are nearly in the ecliptic. So we don't have to design such missions. Maybe it could be interesting to observe the sun on such an orbit, because such a orbit or such a flight path would give us the opportunity to watch the poles of the sun. But it's very, very fuel consuming and difficult to design. Yeah, now we are at the question, how can we control a space probe actively? How can we reach another orbit? In principle, you have the following situation. If we want to change from one orbit, orbit 1, to another orbit, orbit 2, because we want to have our space probe, our space vehicle, in a new orbit. Now we consider again an Earth-centered orbit. What do we have to do? First of all, we know that a rocket is burning very fast. It's burning within a few seconds, and it gives an enormous acceleration of the space probe. That means within a few seconds, we may change the velocity state of the space vehicle enormous, but in these few seconds, of course, the position of the space vehicle does not change remarkable. That means we have burning, assuming a very short burning time, then the change of the location of the space vehicle can be neglected. So under this assumption, we have the following situation. Then we can change the orbit from 1 to 2 only in this point here, where the two orbits are intersecting. So here we have the intersection point of the two orbits. Put it a little bit darker here. And what we have to reach is a new velocity, which should be the respective velocity for orbit 2 at this point. That means we have to apply a rocket thrust here, which increases the velocity or changes the velocity by delta v. And of course, we obtained a new velocity v2, which is then given by a simple vector addition. And this guides us to the orbit 2 here. Well, that's the principle of a so-called impulsive orbital maneuver. But of course, do we have to do if the two orbits don't intersect, as here in this point? For example, here, if you have a low Earth orbit, for example, and you want to reach a geostationary orbit. A low Earth orbit has an altitude of about maybe 300, 400 kilometers. The altitude of a geostationary orbit is about 36,000 kilometers. So how can we get a space probe from this orbit to this orbit? So here we need two maneuvers. We have to accelerate first here in some point. Of course, we can put the rocket thrust laterally or in flight direction. It's better to apply the rocket thrust in the flight direction. That would lead to this orbit here. If we increase the velocity here, then we get a more eccentric ellipse. If we change nothing, then we would come back here to the original point. But here we have a transfer orbit which intersects the target orbit at this point here. And then we have to apply a second thrust maneuver, impulsive maneuver. Here we arrive with a velocity in this direction. We have to apply a rocket thrust, which moves or brings us to this final geostationary orbit. So of course this would be a rather fuel-consuming maneuver, because the second maneuver here, in the second maneuver we have to apply a lateral thrust, which is not in flight direction. From the energetic point of view, it's always the best to accelerate in flight direction and not laterally. So what can we do? We reduce the first thrust a little bit so that we arrive here also at the target orbit with a flight velocity which has the same direction as the target velocity. So here, if we do nothing, then we return here to the original point. If we apply a second thrust here, we can apply it also in flight direction, which brings us to this geostationary orbit. So this transfer from a low Earth orbit to a geostationary orbit is called a Hohmann transfer. That's the most basic maneuver in orbital mechanics. It's very, very important, and it's really often used. So this is called the Hohmann transfer. It's was found by Walter Hohmann. This was a German civil engineer who was fascinated by such questions, but he was actually not an expert in this field. He was a civil engineer, but made some important discoveries here in the field of orbital mechanics. Well, for such a Hohmann transfer, we can do some computations. The question is, how large is the velocity increments, or the sum of the velocity decrements in these points P and A for such a transfer? As you can see in this diagram, if we we want to come to a geostationary orbit, at least approximately in this point here, we need a velocity increment of about 4,000 kilometers, or 4 kilometers per second, or 4,000 meters per second. So these two increments are 4,000 meters per second. So that's much less than this here, as I showed you before. And the flight time for such a maneuver to the geostationary orbit can also be computed. It's about 5 hours. Well, that's the Hohmann transfer. Well, yeah, you can also relate this velocity increment delta V to the amount of fuel you have to use to accelerate the space probe. Here this is the so-called Tsiolkovsky equation formula. U is the exhaust velocity of the fuel. M0 is the initial rocket mass before ignition. Mf is the final rocket mass after burning. And if you prescribe the delta V from orbital mechanics, and you know the exhaust velocity for your fuel, for example, if you use liquid oxygen and liquid hydrogen as a propellant, then you have an exhaust velocity of about 4,500 meters per second. So this U is known, and then you compute from this equation simply the amount of fuel. That means the relation of initial rocket mass and final rocket mass after burning from this relation. For example, if you want to carry out such a Hohmann transfer I showed you before to a geostationary orbit with this propellant system of 4,500 meters per second, then you see that the relation of the initial rocket mass and the final rocket mass is about 2.44. That means after burning, the mass of the rocket, or let's say before ignition, the rocket mass is 2.44 times the mass after the burning. You can, of course, also compute the amount of fuels from this relation. That means that 60% of the initial rocket mass must be fuel. The rocket mass consists of fuel, about 60%. It's enormous. So imagine a car which consists of 60% fuel. It's not usual. This is other dimension. Now, our original problem was to design a flight path to Mars. And so we have this situation here. We see the Earth and the Mars traveling around the Sun on nearly circular orbits. So this has a lot of to do with this problem here, as you can see, where we want to travel from a low Earth orbit to a geostationary orbit. And of course, the same idea, we can use the same idea for this problem here. and to use a Hohmann transfer to get from the Earth to Mars. But of course, this is a little bit more complicated because we are starting within the sphere of influence of the Earth. So the first flight or first mission phase will be a mission within the sphere of influence of the Earth. So we start in a near Earth orbit, maybe a few hundred kilometers above the surface of the Earth. Let's say we get in this near Earth orbit by means of a large rocket, starting, for example, in Cape Canaveral. So we arrive here in the near Earth orbit. Then we have a space vehicle which has additional fuel and additional rockets. Now we can apply a start velocity increment, delta V start, which brings us to a, let's say, hyperbolic orbit that reaches at some point the sphere of influence. And at the sphere of influence, we must have the appropriate velocity V1, which must be appropriate in order to get to this Hohmann transfer in the solar system. Actually, this Hohmann ellipse is a flight path in the solar system. So this start velocity here must be the sum of the Earth velocity and this arrival velocity V1, which we have at the sphere of influence with respect to the Earth. So VE plus V1 must be exactly this velocity which is necessary for the Hohmann transfer. And in the, well, then we are moving several months on this orbit here, on this trajectory. And finally, we are approaching Mars. And now what will happen here in the final phase? We are here on this elliptical orbit. And due to the second law of Kepler, we are decelerating here when we approach this point here. On the other hand, Mars has always the same velocity, and this velocity is larger than this approach velocity here on this orbit. That means Mars is coming from this side with a larger velocity than our space probe has in this point, and it catches the probe on the side of the sphere of influence. That means the probe enters the sphere of influence of Mars on this point. Mars is moving in this direction. It's the arrival phase here. And it enters the sphere of influence in this point and then moves on this, let's say, hyperbolic orbit. If we do nothing, then we would just approach Mars and leave Mars again. But if we want to stay at Mars, then we have to use again a rocket to decelerate the probe in order to get to a low Mars orbit here, for example. So for this mission, we only need two rockets, or have to start rockets 2 times. First, we need the delta V start, which must be, of course, appropriate to get the right velocity here. Then we simply fly here on this orbit, reach Mars sphere of influence, enter here the sphere of influence, and then we have to apply the delta V brake. That's also a velocity increment which has to be produced by a rocket thrust. And finally, we are here in the Mars orbit. Well, you can, of course, compute all this velocity. We can compute the delta V start and the delta V brake from orbital mechanics. We can then compute the amount of fuel we have, which we need for this maneuver. And of course, we can also compute the exact launch position here, which is necessary to arrive in the Mars orbit here, because this point here must be appropriate to obtain to get on this flight path here, and then we have to look that we enter the Mars sphere of influence at a correct point here, in order to get the perigee or peri-Mars, we have to say, at the right height here. So this is, of course, lots of things to control here, but the most important one for the first feasibility study is to compute the delta V start and the delta V break, and that's rather easy. You can compute this from basic orbital mechanics and from simply from the energies of this orbit here. So here you see the result for the first mission phase from the low Earth orbit to the sphere of influence. We only need a few days. The impulse is 3.58 kilometers per second. It's not too much. And if you compute the amount of fuel you need for this is always the fuel related to the initial mass m0, then we have 55%. So for this first burning maneuver, the rocket must consist of fuel of 55%. Well, then we get to this interplanetary flight path here, sphere of influence of the Earth to the sphere of the influence of Mars. This, of course, takes much more time. It can be computed exactly 0.71 years. And we don't need fuel for this mission, of course, because the space probe is just governed by the gravity field of the Sun. And for the final mission phase from the sphere of influence to the Mars orbit, this takes also only a few days. We have to here apply an impulse of 2.1 kilometers per second, and this corresponds again to a fuel amount of 70% related to the initial mass of the rocket from the starting position here. So these are the basic data for such a trip to Mars. We see the trip takes approximately 3/4 of a year. And if you add this, about 72% fuel related to the initial mass. So one question is left. When can we start? Of course, there's one problem. If we start here at any time, it's not sure that Mars will be here at this point when we arrive at this point here, because Mars is in this orbit, and when we are here on this point, Mars should also be there. So then, otherwise, the journey would not be very interesting. So what does this mean? If Mars is in this position at the launch time, and Earth is in this position here, then we have to look at this angle between the two planets, which must have a correct value, because the time we need for the Hohmann transfer here must be the same as the time for Mars to get from this position to this position here. So as it turns out, this angle must be 44 degrees. If this angle is not correct, then Mars will not be there at this point. So the question is, when does this angle has the correct value? What we know is that Earth is moving faster around the Sun than Mars. And this is a result of Kepler's third law. So the angle between the two planets is changing. And what we need is the relative angular velocity for these two planets. It's easy to compute from the orbital periods of Earth and Mars what is the angular velocity of the angle phi here. Now the period of the Earth is of course 1 year. The period of Mars is 1.88 years. And the period of the relative angle between the two planets is called the synodic period. It's a basic parameter in astronomy. You can compute a synodic period for every couple of planets. And there's a simple formula you certainly can derive if you are a little bit familiar with mathematics. then the formula is simply this one here. The formula for the synodic period results from the period of the Earth and period of Mars. And this is 2.14 years. So within 2.4 years, this angle phi changes about 360 degrees. What we can notice is that the closer the periods of the two planets are, the longer the synodic period will be. So if T1 and T2 are nearly the same, then TS will get very large. Unfortunately, Mars and Earth are the closest planets, so they have nearly the same period. And so this synodic period is rather large, but 2.14 years is not too large. Actually, we have to wait if you just passed one launch position. If one launch position has passed, then we have to wait for 2.14 years to get the next opportunity for this maneuver. Oh, we can sum up our results here. So the trip to Mars takes, let's say, 3/4 of a year. It requires 72% fuel of the launching related to the launching mass. And it can be launched every 2.14 years. Now, if you look at this fuel, if this amount of fuel, then it's rather a lot, because you have to construct a rocket or a space vehicle which consists of 72% of fuel. It's a lot. It's really a lot. And it's only the fuel for the low Earth orbit to the low Mars orbits. If you want to land on Mars, you need more fuel. And if you want to return to Earth, then you need, again, more fuel. So, and now think of a rocket which consists of, let's say, 90% or more of fuel. It's impossible to construct such a spaceship. It's impossible, because if you have, you can't design a spaceship, let's say, which has a mass of 1,000 kilograms. And within this construction, you have to put in 900 kilograms of fuel. And the rest of 100 kilogram can be used to construct a tank and the rockets, thrust and the waves and all the things, and of course the payload. So this is not possible to design such a spaceship. Actually, no spaceship has ever returned to Earth from Mars, and the only way to return from Mars would be to use or to take fuel from the surface of the Mars. But it's of course also a problem. Then we need a fuel station there, and we have to design such a fuel station within earlier missions, and that might be a problem. So it's not astonishing that the Mars trip has never been realized up to now. Also, all the people are talking about Mars and Mars trips. It's not so easy to get there. At least to get a human being there and to return the human being safe to the Earth. Well, that finishes my short introduction. Maybe it was a little bit more than I planned originally. So I would end this first part now. If you are interested in some more details, then please let me know. So the others who have enough of orbital mechanics maybe may leave the room now, and the other ones who are interested are invited to stay and ask me some questions, and I have some detailed questions detailed slides with more mathematics. So thank you for the attention.